Okay, so welcome everyone. Thanks for joining us today. Today we're very lucky to have Dana Alon from Tel-Aviv University speaking on distance approximation for graph properties. So please begin.
Okay, so first thing is that since it's the first time I'm giving this talk, then and already Tzlil found a typo on the first slide. so please, if you see typos, or maybe just write them down and then you send them to me. Okay, so here goes, and hopefully there won't be too many typos. So also I'll say I kind of contemplated whether I should give a more like survey-ish talk, or at least talk about distance approximation in different contexts. And then I found that I was kind of spreading too much. So I'll talk mainly about one result, but there'll be quite a bit of background. So in this background, I'll kind of, take a side tour a little bit. I'll say something that is not specifically about the result. And this way also there will be also kind of we'll give you more background about then the context. Okay, so let's start with the general context. So I'll be talking about sublinear algorithms. So what do I mean here? Because there are various types. We have query access to some object O, and we want to perform some computation that is approximately correct. We want to do it with high probability here will be constant. We can boost the probability if we like, but it'll be simple for me to think about it high constant probability. And we want to make as few queries as possible. So just a little illustration. This blob here is the object, and this is us. And we perform queries, and we do some computation, and then we output something. So to define this task precisely, then we must specify quite a few things. We need to say, what is the object we're interested in? What is the query access? What kind of computation we want? And what is our notion of approximation? Okay, so let's start with saying, kind of, we'll go in more narrowly from this, from sublinear algorithms to property testing and distance approximation. So the title of this talk is about distance approximation, but really it sits beside property testing, and to have the right to the right context, we really have to talk about both until I talk about the new results. So in property testing, the task, I'm talking now about what is the computational task that we want to perform in a sublinear manner. It's approximate decision. So that kind of sounds like a first hearing. What do you mean decision is yes or no? It can't be approximate. Well, what we mean here is that we want to distinguish between objects that have a certain property and those that are far from having the property. And far is with respect to some pre-specified distance measure. And in distance approximation, the task is to actually approximate the distance to the property. Okay? And there's also a notion of tolerant testing, but I'm just mentioning it here in case that sounds more familiar maybe. They're closely related, but I'll be talking about distance approximation. And in both, I'll also stress that for both, we allow small constant failure probability. And to define tasks precisely, we still have a few things to specify. But maybe I'll stop once in a while to see if there's a question about the general setup before I kind of go more inside. Okay. And as I said before, you can just barge in and talk and just unmute yourself, say something, and that's fine with me. Okay, so I'm going to talk about property testing and distance approximation. Now I'm going to talk about the type of objects that I'm interested in, and then also about the query access, the distance measure. So I'll talk about graph properties, and I'll talk about in the adjacency matrix model. Okay, so first, when I say graph property, I just mean it's a property that is invariant under isomorphism. And it'll be convenient to me when I say property, I think of the set of graphs that have the property. So then I'll say G belongs to the property, then this is that it belongs to the set of graphs that have the property. Now, okay, so we've decided on what the object is, but there are various models when we talk about graph properties, and they vary in the type of queries and the distance measure. It's related to the way they're represented. And here, I'm going to focus only on the adjacency matrix model. So in this model, the graph is represented by n is the number of vertices by an n by n adjacency matrix. So just if there's an edge between u and v, there's a 1. If there isn't, there is a 0. Now, then what are the queries we are allowed? So this is kind of straightforward given the the representation, we can ask whether there's an edge between U and V, and we get yes or no, depending. It's a probe into the adjacency matrix. And what about the distance measure? The distance measure is the fraction of entries in the matrix that we must modify to obtain the property. And we denote it by delta GP. So again, if the graph has a property, it's just 0. And if it doesn't have the property, then we need to modify, add or remove edges. And here the fraction is with respect to the size of the representation of this object with respect to n squared. And again, kind of in passing, there are other models that in which both the queries and the distance measure are different, but this is the model I'll be interested in. So now, once I said what are the objects, what are the queries and distance measure, let's just kind of recall how does it fit when we talk about property testing and distance approximation. And from here on, I'll use the shorthand PT for property testing and DA for distance approximation. So the property testing algorithm, and it's given query to the adjacency matrix, and it should decide whether the graph has the property or whether it is far. So we have to, the fraction of entries we need to modify is bigger than epsilon. Epsilon is the given distance parameter. And the distance approximation algorithm should actually output an estimate of this value. So it should output delta hat, where the difference between delta hat and delta is at most epsilon. Okay, so one is decision and one is approximation. Okay, questions?
Dana, in the no case, do you also require an approximation or not?
So you say when it's in the property testing, when it's far?
When it's far, yeah.
When it's far?
No, I mean for distance approximation, in the case where you have the far, in the far case.
No matter what it is, it's not only that if it's not too far or it is far. I mean, there's no promise here. In property testing, we see it also, I said it's approximate decision. It also can be said decision with a promise. So so the promise is that either it has a property or it's far. In the middle, we don't really care. So here there's no promise. It can be whatever it is. We want to approximate it well. Okay.
So the two versions you stated, they're not comparable, like not one.
Oh, okay. So good point. And we'll see. So distance approximation, if I'll say it in one sentence, then I'll say that distance approximation is, I would say, harder or not easier than property testing. But there is a kind of there is a subtlety here, is that whether when you define property testing, do we allow two-sided error or one-sided error? That's so here when I type here in this context, it will be two-sided. You can err in both directions. Also, if it has a property, also if it doesn't. And then in that sense, it's so if you have a distance approximation algorithm, then you have a property testing algorithm with two-sided error. Okay, good. Any more? Okay. So just this is where we stand, and now I'm going to start giving some background on both property testing and distance approximation. And I'll say from the start, it's not exhaustive, and it's also not chronological. So it really is more to serve my purposes. So in the sense of putting the result I want to talk about to say, what is the most relevant background. There are lots of works on property testing in this model, and I'm going to say what is most relevant for me. So first again, it's not the first result chronologically, but it's the most general result that is known by Lund, Fisher, Newman, Shapira. And maybe it's something you have heard of, maybe not. And the title of the paper, it's all about regularity. There's a subtitle, but what they show is they give a characterization of all the properties that are testable with a number of queries that depends only on epsilon. So the point here is there's no dependence on the size of the graph, and it's only a function of f of epsilon. So I won't talk about this characterization in detail. It's non-trivial. But what I'll say is that it uses the regularity lemma. So the point here, it's very general. It characterizes, so the both directions. But because it uses the regularity lemma, this function f of epsilon, again, only depends on epsilon, but it's pretty high. So it's a tower of height polynomial. So again, if you don't know what the regularity lemma, it doesn't really matter right now, but I'll just say, but if you do, then kind of it will be familiar, this expression of the tower. So again, general result, but with very high, so tower, 2 to the 2 to the 2, and the height is polynomial 1 over epsilon. And also,
Anna, can you give an example of these kind of properties?
Oh yes, so we'll see lots of properties in a minute. So we'll see. No, but I'll throw for now. Say
okay.
So actually, you can some of the properties that I'll mention are actually have better complexity, like colorability. You want to know whether the graph is. Let's even start with bipartite. You want to know whether the graph is bipartite or far from bipartite. You want to know whether it has no triangle or whether it's triangle free or non-triangle free. So these are kind of two basic examples that will also come up as we go along.
Thank you.
And I'll mention there was an independent result that got also characterization using graph limits. Okay, so this was property testing, general result, but a bit costly, but very general. Now, when we go to distance approximation, Fisher and Newman showed actually also a very general result about distance approximation. They showed that every property that has a property testing algorithm with dependence only that depends on epsilon has a distance approximation algorithm also with dependence only on epsilon. And here the complexity is even higher. So Wowzer is like a tower. This is kind of a recursive definition of towers of towers. So this is, if tower is high, Wowzer is like really high. But still, it is, again, it says something very general, only depends on epsilon, no depends on n. And if you want general, but maybe slightly less general, then there are results for I'll use my cursor, this will be good. So for pretty general, but still more restricted monotone properties, the properties that are maintained under removal of vertices and edges, and hereditary that are maintained under removal of vertices, still it's better, not Wowzer, and but still it's towers of height. The best you can get is tower of height polylog 1 over epsilon, which is in great improvement, but still pretty high. So general results. This is kind of what you get from here. General results come at a cost. Okay, so then you say, well, you want these big functions. You don't want to hear about these big functions. You want polynomial, or even here, since those functions are so high, even exponential. One level of exponent is fine, but really we would want poly 1 over epsilon. And here, so first I'll talk about what is known about testing in this for poly 1 over epsilon, and then I'll talk about distance approximation. So for testing, now I'm going back in kind of in history to the first paper that explicitly talked about testing graph properties in the adjacency matrix model. And here in this paper, we showed actually that you can get poly 1 over epsilon query complexity property testers for a general family of partition properties. So I won't define this family here. I will actually later talk about a subfamily, so you'll get a feel for what I mean here. And here I'll just say that it contains k-colorability, row cut, which means do you have a cut of size of at least row n squared edges crossing the cut, row clique, do you have a clique of size at least row, and so on. It's a big family, but it contains pretty much, I don't know if you say the natural partition properties that you would like, you would be interested in. So you can get poly 1 over epsilon for this family. Alone looked at H-freeness, here non-induced. Again, you want to know, is the graph H-free? So you're given a constant size H, say a triangle. I'm not saying this, so we'll see what I can say about a triangle. And you want to say, is it free from this subgraph? And what he showed is a dichotomy. He showed that you have a poly 1 over epsilon. And again, here I talk about queries. Maybe that's a good point to say this. I'm interested in not that I don't care about time, but queries are really the main issue. And definitely for the partition properties, since they are related to hard problems, then you can't expect to have poly 1 over epsilon time. So focus is really is queries. Say, how much do you have to look at the graph to make a decision? So now returning to Novalon's work, so he showed that if the subgraph that you want to be free of is bipartite, then you have a poly-one-reversal testable algorithm. If it's not, then you don't. That's really, and what is kind of striking here, I think, is again for people who kind of were maybe people working combinatorics, maybe they wouldn't think it's so surprising, but I think from outside it's even like the simple property that I mentioned before, triangle freeness. What's the big deal being triangle free? You really must have super polynomial. On the other hand, if you have like even a small but bipartite, you have a C4, then it is poly-one over epsilon. So these things kind of show you it's not really clear what's easy, what's hard. And still one more thing, as I promised that I'll take small sidetracks. So triangle freeness, there is a super polynomial, but still there's a big gap. Even if somebody showed something, exponential, that would be, or even double exponential would be interested because the upper bound is much higher. It's a tower of log 1 over epsilon. I think this is the best known result right now. Okay. Now, I said that Alon talked about non-induced H-freeness. And with the Shapiro, they worked on induced H-freeness. And here what they showed, that induced H-freeness is not poly 1 over epsilon testable for every H with very few exceptions. So here it's, well, in the non-induced case, you have a dichotomy, some you have, some you don't. Here it's really almost everything, there is a super polynomial lower bound, but there are these P2, just an edge, P3, path of length 3, path of length 4, and a cycle of length 4. These are the only ones which were, they showed there isn't a negative result. So this is kind of, it's mostly a negative result here, but it leaves open kind of a few positive questions. And indeed, and there are complements. So this is kind of natural that if you can't do one, you can't do the other. So, and what about positive? Okay, that was pretty negative. What about positive results for these specific graphs? So other P2 is just an edge, so that's very easy. But also all the other ones, P3, P4, have poly 1 over epsilon. C4 has exponential poly over epsilon. And chordality, which I'll talk a little more at the very end, and I mentioned it here, it's a subset of C4 freeness. I won't say exactly what it is now, but I'm interested in it, and so I mentioned it here. And this was in a sequence of several works. So respectively, kind of each one of these was shown in a different okay. So just to kind of say where you don't have to remember. Whenever I'll need one of the things here in the background, I'll remind you. So you don't have to remember. But basically, there's strong negative results, but there are also some positive results for these specific subgraphs of interest. Okay, so this was testing. What about distance approximation? Again, poly 1 over epsilon. So here there is less is known. So now from this point on, and I'll use GGR and instead of the 3 names. So my rule is first 2 times you get a name, afterwards you don't. And so the focus in this work was on property testing, as I said, but as a subroutine, the paper includes an algorithm for approximating the size of the max k cut. So you want a partition to k sets, and you want the number of edges to maximize the number of crossing edges. So here you might be a little worried, say, hey, just a minute, this is a hard problem. You might have been worried before also about this with the testing, but note here that the type of approximation that we get here is within an additive epsilon n squared. So it's not a multiplicative approximation. So that's one point, and again, and also it's poly 1 over epsilon queries. And this says, in particular, it says maybe a little more, but in particular, it says, remember we talked about k-colorability as one of the partition properties. So we do have poly 1 over epsilon query distance approximation for, kind of well-known natural property of k-colorability. So we have, this is one, sorry, one positive result that we have for distance approximation. Okay, now I'll say a couple of things that are kind of immediate, but still we have to kind of see where we stand. So P2 is just an edge, so that's really trivial. But actually, you can transform the results from the testing to distance approximation for all bipartite H-freeness and non-induced, basically by approximating the number of edges. So this is easy. On the other hand, this is related to the question that was asked before, all the hardness results, since they hold for two-sided property testing, the hardness results for property testing also transform. So we get this kind of for free hardness to hardness. And one more thing that I mentioned on the positive side. So one of the papers that actually appeared before, Hopen et al., their result with some additions applied distance approximation algorithms. Now this is going to be important for my context. Remember those properties before? P3 and P4 freeness induced with exponential in poly 1 over epsilon, and for C4 freeness and chordality with double exponential poly 1 over epsilon. Okay, so I'll remind you of this. So this is kind of, I think this is, I don't have here. So this is what we know about distance approximation. We know for K colorability it can be done in poly. There are some easy things that can be done. And for those properties that we don't have a lower bound for polynomial, then there are results, but they're at least exponential or even double exponential. Okay, so this is where we start coming in. And again, I'll remind you. So now I'll say what our results in, and then I'll pause to see if you want me to remind you of something. Sorry,
yeah,
yes,
just
please.
a quick question. Sorry, I may have missed this, but how does n exactly enter in all of this? I mean, we keep talking about
this is great.
epsilon.
And again, don't worry if you, I think it's really important, even whether I said it explicitly or I didn't say it, I think if something, you miss something, then I do want you to stop me, because I know I find it, it throws me off and then I can't concentrate. And I think also other people probably did. So in any case, with that being said, so n is the number of vertices, but in terms of the complexity of the algorithm, the number of queries, it does not, in all of these cases, does not depend on n. So there's no, it only depends on epsilon. So basically, you look only at a very small subgraph. Based on that, you make decisions about the whole graph, and it does not depend. And I mean, it scales. I mean, there's no problem of scalability with n. There's only dependence on 1 over epsilon.
Okay, but then a quick follow-up on that is, if I allowed the algorithm to depend, say, logarithmically on n, can the dependence on epsilon be?
This is really a good question. So it's quite interesting that actually there are hardly any results in property testing in which the dependence on n really gives you something. But I want to be careful about this. I can't really say that I'm sure that you can't get a trade-off. I have to be knowing, I'll be careful about this. If I remember kind of asking myself, I'll say two things. One is, there are the only results that actually have an explicit dependence on n in the dense model, not in the others, are for isomorphism. That's there are results that depend on n, they're lower bound, so really you must have a dependence. All other results in this model do not. So then you ask, but maybe you can do some trade-off, and here I want to be careful. I remember asking myself, and I don't remember if the answer was that in the end that I don't know if you can have a trade-off, or whether it was. And maybe one more thing that I'll mention: there are non-natural. So you can get a hierarchy. So this is maybe when I think about properties, I think about natural ones. But there is work that shows kind of for a hierarchy of that for every complexity you have a property that is. This is its query complexity, but it's for made up problems. So it's not, so still I think it's good to know that there is this hierarchy, but it's not for natural ones. So there are results in which there is dependence on n, but in a non-natural way. Okay, so this is kind of, so I hope I answered.
Yeah, thanks.
Okay.
So maybe another question on this topic.
Sure.
So the distance is normalized by n, right?
Right, by n squared. Right.
By n squared. Okay.
Right.
So
this is really.
Okay. Thanks.
Yeah. So this is really important because it means it's meaningful for dense graphs. So if you want to talk about sparse graphs, then you should work in a different model, and the results there are quite different. It's also in the testing. Maybe I'll, I said that in the worst case, if I won't have time for all I wanted, that's okay. I think I'd rather tell you things that you're interested in. But I think, something, for example, for the property I mentioned before of two colorability, that is bipartiteness. So if you talk in this model, you need just a small polynomial, it's 1 over epsilon squared queries, suffice for testing. So really, you look at a very small subgraph, and if you can distinguish between being bipartite and being far, according to the small subgraph. On the other hand, if you want to talk about sparse graphs, so in sparse graphs, you will normalize. This is the natural normalization will be with respect to the number of edges, not n squared. You know, if it's sparse, then n squared, that it's not meaningful. So if you do that and you work in a different query model, then you suddenly have a dependence on n. There's upper and lower bounds that are related to square root of n in the more general model. So it's model dependent, density dependent. So there is, but definitely this is really important that it's with respect to n squared, meaningful for dense graphs. Okay.
Very cool. Thank you.
Yeah, sure.
Can I ask, what is a query? A query just check whether an edge is there or not, or you can do something more sophisticated?
Yeah, that's the query. The query here in this model is just you give the name of two. So you know n, so let's call the vertices are named 1 through n. You give the oracle ij, or you probe into the adjacency matrix, and you ask, is there an edge or isn't there? Okay. Basically, the type and the type of things you can do is you can do a little more, but basically you take a sample of vertices and you look at the induced subgraph and you decide based on that. And this is as opposed to other models in which you can do more sophisticated things like, you know, random walks, BFS, stuff like that.
Are the queries adaptive or not?
So they may, okay, so they may be, you are allowed, though here adaptivity won't be relevant. Okay, again, if you want to really, once you get into the subtleties of like what polynomial of 1 over epsilon, adaptivity may help. But if you're not, if you know polynomial is enough to you, square it, so adaptivity is not. But if you really, you start going to and actually I think that's interesting too, but here we're talking about big polynomials, sure. So it's and adaptivity is not really and again in the other model it is, because you walk in the graph, you're adaptive by nature. You have to, you know, you get a neighbor, you want to continue, you have to know its name. So but here, yeah, it's not adaptive.
Thanks.
Okay. Okay, so what are results? So what we do is we describe a kind of methodology for designing distance approximation, algorithm. It's based on a notion of property covers, which I'll talk about. And then we apply this to obtain distance approximation algorithms for P3, P4, and chordality with poly 1 over epsilon queries, and for C-freeness with exponential and poly 1 over epsilon queries. So now this is a good point to compare, to remind you of how this compares to previous work. Also, one important thing here, since I talked about H-freeness, both induced, non-induced, there's a difference. So here I'm talking about induced, right? Induced freeness. So, but I won't say the word induced, I'll just say free. So one thing to point out here is that it matches the property testing results for these properties. So same complexity. Again, not exactly the same polynomial. Even in one case, we get a better polynomial, but just because we were, I mean, it's not, in that result, they didn't make an effort. It just happened that we got to build better polynomial, but that's not the main issue. But it's really the same structure. For these three properties, there's poly testing, poly distance approximation, and for C4, it's X poly. And if we compare it to what was known for distance approximation, then we improve exponentially. Or in one case, even a little more than that. So just here, I'll remind you that the previous results show that for P3 and P4 it was X poly, we get poly, and for C4 and chordality, they get double X, and here even for chordality, we get poly. And so it's both matching for testing, and it's an improvement. Okay, so question at this point before I start, I jump into how we do this.
Yeah, P3 freeness, does it mean counting P3 number of P3s in the graph?
No, it's not. It's not counting. It's not counting them, but it's rather. We'll see in a minute. 5 minutes. I'll get to. You'll see what P3 is. It's different from counting them, right? Because the measure here is the number of edges that you need to remove or add in order to make it P3 free. It's a different notion than counting as compared to the number of P3, which is with respect to n cubed. So it's a different It's a different notion.
Okay.
Okay, any other questions?
I mean, maybe you'll get to this later, but I mean, is it a coincidence that you're matching the result for property testing, or are you doing some sort of reduction to property
okay,
testing?
So it's not a reduction. We do build on these underlying combinatorial structures, which we use and we're also used in the property testing, but it's not by reduction. So it wasn't clear that even if we use those properties, it will really give us the same. So this is, and actually I would say we hoped at some point that we actually will improve for the C4 freeness. We kind of thought we had something that will even give the poly one for epsilon for C4, which is the only one among these that is exponential poly. Yeah, so it's not by reduction. So again, I can't say exactly coincidence because of the structures, but it's not by reduction.
Okay, thanks.
Okay, so let's start with, okay, so let's see what will be the structure. Let me look at the time, good, okay. So I'll start by talking about property covers, this notion, and then I'll show how we use them in order to get our results. Well, I'll give a couple of examples. Okay, so now I'm going to define this notion of property cover. So P will denote a property, F a family of properties, epsilon is our distance parameter. And we say that F, the family of properties, is an epsilon cover per P if, now it's going to appear in a statement, but I'll have an illustration in a minute. So some people prefer to see things in kind of formal form, some illustrations, so I'll give both. Okay, so the first thing we want that the cover will have is that for every graph in the property, this is our property that we want to cover, there exists a property in the cover such that our graph is close, epsilon over 2, close to that property. So that's one thing. And the other thing is kind of in the opposite direction. For every graph G prime that is in the union of all these properties, we want it to be close to our property. So let's look at, I think, an illustration. For me, at least, it helps. I need to concentrate. When I have more than one quantifier, usually I need to concentrate. Okay, so this illustrates P. That's our property. And now this is here. I have 3 properties in my family F. And what do I mean that they cover here? Basically, well, when you look at it, it seems like, kind of the symmetric difference is small, but it's not exactly that. So let's see what it is exactly. So first, for the first condition that we ask here, we say for every G in the property P, we want there to be a property P prime in the cover that it is close to. So it's not really nicely covered. It's not really covered by the cover. So it's not that everybody in P is in some property in the cover, but it's close to it. And we also need the other direction. So we also need to show, we need the second condition. If G prime is in some P prime, again, it doesn't necessarily have to be in P, though in some cases it will be, but again, it is close to P. So in both directions, they're kind of semi-tight cover. That's kind of the idea. So any questions about this definition? Because this will be something that will be important for me. Okay, so I'll return to it if you'll want to. I'll return to this picture if you need to again. And now we have a claim that is not complicated, but it will be really useful for us. And I'll state it roughly. And the reason roughly, because if I state it exactly, then it will be really tedious. So I'm kind of, brushing kind of, the quantifiers aren't precise. A few things aren't precise, but I think it's more intuitive when it's approximate this way. So what does it say? If I have a graph property P, and I have F of epsilon, on purpose I want to remember that it depends on epsilon. For different epsilons, the covers have to maybe different. F of epsilon is an epsilon cover for P. So what do I know? Suppose I have a distance approximation algorithm for every P prime in my cover, and it makes Q of epsilon queries. Then the rough statement is that I have a distance approximation algorithm for my property, and it makes roughly the same number of queries up to a dependence, logarithmic dependence on the size of the family. So this is kind of, if you want, you see this log and you say, oh, that's kind of, log union bound. Yes, it comes from basically a union bound. And so basically, if I want to say in 2 words how this is proved, it's a combination of a union bound and triangle inequalities. So this is, so in order to see how it works exactly, then one has to write the quantifiers precisely and a few other things to see why can we use union bound and so on. But this is roughly, will be roughly the idea. So the claim again, if I have a cover, then I'm doing pretty well. If it's not too big, again, I'll depend on the size of the cover, and I have a distance approximation for everybody in the cover, then I'm pretty I'm doing pretty well. I can get, and I want to say another thing, this in retrospect, when looking at previous works, even those with the regularity lemma in the distance approximation, they had implicit covers, but they weren't explicit. And also, it's not easy to go into and define the covers there, but there is, so it's kind of one of the things we're making it explicit. And also, it might remind you of things, or I think it's pretty different, but at first, first reading it, maybe it's a little like, like an epsilon net, but not quite. But it reminds you of other things that probably you've seen in the past. So it's a pretty natural, not complicated notion. Maybe this direction is less intuitive, but it's important here for one of the triangle inequalities. Okay, so questions about the statement, though I haven't proven it.
Can I have a question?
Yeah, please.
I think I can understand that if this is non-adaptive curious, because basically it's a union probabilistic bound. But if it's adaptive, I fear to see how
you're totally right. That's part of the roughly. So actually the precise thing, and which is relevant, this is not a general statement that is not for, so actually the more precise one is exactly you're totally right, using the non-adaptivity of that really what these algorithms for these properties do. They take a subgraph, they sample vertices uniformly at random, look at their subgraph and decide. So the queries are not adaptive. And this is definitely, you're totally right, because otherwise it would be, you wouldn't have a log factor. You would have, so the point here is that since they all, in terms of their queries, not in terms of the decision, in terms of their queries, they do the same thing. They take a sample. So it's enough to take a bigger sample so that we can reduce the failure probability of each of them. So this is, you're totally right. This is, so this is one of the things, yeah, that I'm hiding. The other thing is the quantifiers here with epsilon. So this is even more, this is a crucial thing. You're right. And this is something that I'm using that works out for in property testing of graph properties, but maybe problematic elsewhere. So it's not, I can't say it's totally general. Yeah, so thanks. Any other questions? Okay, so good. So now we made an important step in the sense that what we want now is covered. So we have our properties, and we want to find these families that are known to be easy, or we can show that they're easy to get a distance approximation. And the families I'm going to talk about, I'm going to call them semi-homogeneous partition properties. It's a long name, but it's not very complicated. And now I'll remind you, earlier on, I said that GGR talked about partition properties. These are a subclass of these properties, and they are pretty easy to define. And on first thing, I find this kind of interesting. So that there's a difference, P3, P4 freeness. What does that have to do with partition? So we'll see. But I think that's kind of nice that the family that covers doesn't sound like something that is related to the property on first hearing, and then you'll see why it is. Okay, so what are these properties? So each property in this family is defined by an integer k. And k, think of k calculability, k cat, and a symmetric function. So here it is specific here. The function is from pairs ij, I and j each in k, to 0, 1, and bottom. We'll see what this means. And so a graph has the corresponding property, which I'll denote by p sub phi. So phi is my function that defines the property. And so it has a property p sub phi. If there exists a partition, here's a partition of the graph vertices into k sets. Again, you'll have an illustration soon, such that for every ij, what holds? If phi ij is 0, then there are no edges at all between vi and vj. If phi ij is 1, then there are all edges. This is the homogeneous notion that there is a kind of, for every, also for IN itself. IN can be, if II is 0, it's an independent set. If II is 1, it's a clique. And then you say, what about bottom? That's the semi. So you're also, if there's no constraint, then you can have whatever you like. So we need that. So one thing to say before I show an illustration. So one thing to say here is that K colorability is a good simple example for this. Basically just phi I is 0. You have K sets, those are the colors, 0 inside, and then other than that, you can have whatever you like. But more generally, let's say, I hope I'll explain kind of the texture codes here for this example. So here I have K equals 3, so it's V1, V2, and V3. And suppose that here, this is a clique, this is an independent set, this is a clique, and I can do that with phi I. And between 1 and 2, it's a complete bipartite graph. Between 1 and 3, there are no edges. And this little wavy thing represents that whatever you like between V2 and V3. So you can represent here things that are more general than coloring, but they have the spirit of coloring. Okay. So questions about this definition, if you want to kind of digest it a bit. Okay. So when I'll use the notation, SHPPK, semi-homogeneous partition properties of size K. And now there is, what can I say about this? I said, I want a family that will be easy. And indeed, easy, I mean easy by what we know or by what we can show. And there's a lemma saying that for every partition property of this type, semi-homogeneous, it has a distance approximation algorithm whose query complexity is polynomial in 1 over epsilon, that's good, and logarithmic in K. Actually, this logarithmic in K in some of our results is really important. It's not linear in K, but it's logarithmic in K. And this might sound, but I don't want it to sound in the beginning confusing and counterintuitive, because you have to depend on K at least linearly. Well, you don't really, and I think I'd rather not get into this. Why? So maybe I'll leave it to think, and if you want, you can send me email later that I'll explain. I'll just say you can prove this lemma either directly by adapting one of the GGR results, or indirectly by showing that it's related to these constraint satisfaction problems, which takes a little to see, but once you see it, then it's almost that, and using a work that we have before. Okay, so we define these properties. We know that each of them has a distance approximation. So putting this together, our corollary is, if a property has an epsilon cover in this family, and again, the family that is a semi-homogeneous partition property, and it depends, the cover depends on epsilon, also K, the number of parts depends on epsilon, this is important. Then by combining with the claim we had before about covers, then we have a distance approximation algorithm with query complexity depending on polynomial in 1 over epsilon, logarithmically on the number of parts, logarithmically on the size of the family. So this will already, okay, I'm looking at the time, already you can kind of see that this gives us kind of what it helps. Here's a polynomial. Here it allows us that the covers will be pretty big, not both in terms of the family and also the number of parts. So we can the number of parts may be exponential, our result will still be polynomial. And the size of the family will be exponential in poly 1 over epsilon, and we'll still be fine. If it's more than that, then we'll start paying. But this is something that both these things are important for our results. So questions about this corollary? Okay, good. So now that we have in our hands this notion of semi-homogeneous partition properties, a corollary that tells us, just find a cover, not too big, not too many parts, and then you can use it in order to compute the distance approximation. So what we'll do now is we'll see how much time it will take. My plan was to talk about, P-freeness, and there was a question before, so it's good. P-freeness is really, it's easy, but I think it's good to see something easy. And also, since I might not have that much time for the harder ones, then we'll go through this, and then in the time I have, I'll talk about P4 freeness. So it's easy, but it will give us a feeling. things. So I want to go through it kind of in detail, even if it will take us. Okay, so our starting point is a combinatorial fact, I mean known fact. A graph is P3 free if and only if it consists of disjoint cliques. Okay, and this you can check. This you can check for yourself that that this is really in both directions. It's kind of so it's a you know, I don't like giving exercises and talks, but still I think it's a you know, it's kind of a nice and simple one. So it's really easy to check that this is really a characterization of P3. And again, remember it's induced. So, right, so you're not allowed to have this path, but you can have other subgraphs over 3 vertices. So you can have a triangle, that's good. You can have an edge and a separate vertex, and you can have 3 separate vertices. Okay, so then you say, hey, just a minute, you know, why do I have all of this slide? You know, am I not done? I mean, this sounds pretty, you know, in each part is a clique and nothing between them, then, you know, but there's a little catch, because we said we still, if we want to define this as a semi-homogeneous partition property, or even homogeneous, because everything here is, there's no bottoms here, then we'll need a lot of parts in general. In general graph, we'll need a lot of parts, and then we'll have, you know, maybe it's order n parts, then we'll have a dependence on n. This is not what we want. So we can't just use it exactly as is, but if we think a little more, then we have the following claim. The following claim says that, that P3 freeness has an epsilon cover, f of epsilon, where the number of parts is just related linearly to 1 over epsilon. You know, here I was precise, 1 over epsilon plus 1. Usually I'm not that, you know, I don't go to the plus 1, but here it's simple. And even the family is just 1 property. Okay, so we'll see this. So I claim here that using this, it's very much, it is a semi-homogeneous, but the K is too big. So what we want to do is use the cover that allows us kind of to do things approximate to get something that has a small cover, okay, the few parts. Okay, so we're going to, since I said it's simple, the claim, let's just prove it in a few lines. Okay, so what will be the property, what will be the cover I said will contain just 1 property. What will that property be? Then the property will be defined by 1 over epsilon disjoint cliques and an independent set. And between them, nothing between them. So this fits into my semi-homogeneous framework. So this property belongs to, if I use just, again, this is 1 over epsilon cliques plus 1 independent set. So I have, you know, the right number of parts, and it's just 1 property. So the cover is just of one property. But why? So okay, so this is easy to define, but why does it have, why is this a cover? Okay, let's see this in detail. I want to claim one direction of the cover says that every graph in the property that is P3 free is epsilon too close to this property, to some graph in so all I'll do is the following. I'll take my graph, it has many cliques, and I'm going to just keep biggest ones. I'll take the 1 over epsilon largest cliques, and these will fit to my 1 over epsilon disjoint cliques. And I'll remove all other edges. So I'll make everything else into an independent set. And again, here, if you'll check the, I won't do the calculation here, but I removed at most epsilon, and depends here up to a factor of 2, I removed order epsilon n squared edges because I kept the biggest ones. So the total number of edges in all the small ones is small, and I got what I wanted. So this was in one direction. In the other direction, it's even easier. What I mean in the other direction, remember, if a graph G prime belongs to the cover, here the cover is just 1 property, then I want it to be close to my property. But it's actually P3 free, because all I did is I removed some of the cliques. And oh, maybe this is an important thing to say. In this definition here, I'm allowed to have cliques of size 1. Nobody says so. The independent set guys will correspond to just very, very small cliques. And the last thing, and then I'll let you digest a bit and see if you want to ask something. So if I take this cover corollary from the previous page, then I get that P3 freeness has a poly 1 over epsilon query distance approximation, because I said I need a cover. I depend poly 1 over epsilon and logarithmically on k. Okay, that's cheap, and logarithmically on f, that's very cheap. So for P3 freeness, I get by the cover corollary, I get what I want. Okay, so I'll stop for a minute. I want to ask questions about this. Okay, so in the few minutes that I have, I will try to give you, I guess, a taste of P4, and it will be just more to, yeah, let's see what how much time I have and if I have. But suppose I'll stop a little more. Do you want to ask anything about this? Okay. So for P4, I guess what I'll have time is maybe just to tell you what is the underlying structure and something about the ideas of how we, where it is less easy than P3 and what else. Okay, so here the fact is that a graph is P4 free if and only if it has a cotree. So I say, okay, I know, with cliques before, that's fine, cotree. And I'm giving you this new thing. So let me just define what a cotree is. So a cotree, which I don't know why it is, I don't like that name, but it has been used before. I would call it maybe a cut tree, but it's called a cotree. So a cotree of a graph is a binary tree, such that, and again, I'll have an illustration, and I might even add, I'll have an illustration in a minute. There is a one-to-one correspondence between the leaves of the tree and the vertices of G. So basically, the leaves are the vertices of G. And why do I want to call it a cut tree? The internal nodes, each internal node corresponds to a cut in the graph, where the cut is either empty or full. And you know what, let me go to the illustration. I think this is a little easier. So suppose these are my vertices. This is my graph. Now I want to just kind of describe the cut tree or the cotree. So I'm going to build the tree from top down, and there are more than one ways to do it. So I'm going to start with cuts, which I'll do separations, and I'll continue recursively. So I start with one cut, which is a complete bipartite graph between this side and this side. Okay, so I put kind of the internal node. I write one. One reads full cut, all edges. Now I continue, and I'll put the vertices here. A, B go on one side, others on the other side. Now let's continue recursively to this side. A, B, no edges, empty cut. So I put a 0 here. This is the cut here. I put something saying, empty cut. How do I continue now? Between C and the rest, there's more than one way. That's an empty cut. So I put a 0, and I have just 2 more cuts to go. Here we have another empty cut. I have 3 more cuts, and between the other guys, we have full cuts. So this is every P4. This is maybe harder to see why this is true, but every, so maybe at this point, since I have very little time and I need to kind of wrap up soon. So I'll just show you my nice slides, and I'll just say that looking at this again, we have something similar to what we had before. This sounds like, okay, there are these sets, there are these cuts, homogeneous. It sounds like, isn't this a partition property, semi-homogeneous? Again, it is, but unfortunately, it might have too many parts. So the main kind of thing we need to do, and again, I'll just kind of quickly go over this, is show that you can take a big tree, like we had before, many cliques. You can take a big tree, and by more complex modifications, we can make it into a smaller tree by being here, actually removing edges is enough. And just because I like my slides, I'm going quickly, and if anybody wants them, I can send them. And the last thing I'll say here is that for C4 freeness and chordality, and maybe the last thing here I'll just want to say that, okay, sorry, okay, so let's just I'll quickly go through this. There also what is common here, we have an underlying combinatorial structure, so we use this. The problem is it doesn't fit into the semi-homogeneous exactly. So now what we do is that we have based on this, but we need to do some modifications. So for C3 and P4, it's somewhat more complex. We also use this bottom thing, which say, well, why did I need that? We need that. We need to have the covering both directions. And we use also the fact that the K and the size are exponential, not poly. So I have to recap here, and then I'll let you ask questions. And if you wanted me to go back, I'll be happy. So again, we describe methodology for describing distance approximation algorithms. It's based on what we call property covers. And we apply it to get for P3, P4, and chordality poly 1 over epsilon, for C4 exponential. It matches the property testing results for these properties. So it's the same complexity. And it improves on distance approximation exponentially. And it uses something I didn't say in the beginning because I didn't define. It uses a particular family of properties that are partition properties. So some seemingly unrelated, but we find out that very related. And I think the kind of the main open question, this is kind of the last minute that I have. The main open question is, so we said it matches the property testing results, but is this a general thing? And this is related to what Slil asked. So we didn't reduce, but maybe there is something general that shows there's always a polynomial relation or maybe slightly bigger function relation. We don't know this is not the case. Actually, at some point when I talked to Oded Godard, then he said that he thought maybe he can show actually that it's, or maybe I'll say one more thing, that in general functions, there isn't such a, there are properties that are easy, very easy for property testing, very hard for distance approximation, very big gap. But we don't know if this is the case. Maybe it is. I don't really have a guess here. So, but this is, I think, very interesting. What is the relation between them? Is there something general? Probably will, even if it's not the case, what properties does this hold? Maybe we'll need more general covering. And the last little kind of annoying thing is C-freeness. Why we want to get, that would be the last, we would want to nail it down to get poly 1 over epsilon. So at this point, I'll just stop and see if you want to ask me any more questions. Thanks.
Okay, let's thank our speaker by waving our hands in the air since we can't clap. Okay, excellent. Do people have questions? You can just unmute yourself and ask. I actually do have one question. I mean, while people are kind of gathering their thoughts. So I guess just because you brought up the regularity lemma, I guess like in the regularity lemma, I should think of, instead of having a semi-homogeneous partition property, I have I can get a partition, but I need like many different refined levels. Right. So is the power here really that you are identifying properties where like 1, 0, or don't care is enough? I think there's several things here. So first in the regularity lemma, again, it's generality, not only in the application of property testing. In general, it says, every graph and every epsilon, there is a regular partition. Lots of parts, but it's really quite amazing. So it's something you do kind of in advance. Every graph has it. And here there are two things. First, we don't claim that every graph is close to having, so that's one thing. It's things that have the property that we're talking about can be covered in this manner. And also it is really that they are, the covers we use, the family is really much more restricted. It really is. So it doesn't have to be really 0 or 1, very kind of this homogeneity is really very useful here. And that's what it makes it less general, but, and the question, somehow in between, there are also different types of regularity lemmas. Regular partitions are more the stronger, weaker, and maybe there is something here that can be, I don't know, and now I'm making this up. There's some continuity, there's some hierarchy of partition problem. I'm not really sure, but you're totally right that it's much stronger there, and it holds for all graphs. And here we need something weaker. That's the power that we take. Thank you.
So if anybody will want to ask me, so again, I am aware that we spent more time at the beginning, but I think it's, I don't mind that we didn't, maybe it's more important in a sense to understand kind of what are the questions rather than the particular result. So, but if anybody will want me to they can send me email to ask about something.
I have a question. So
sure.
Here your algorithm is deterministic. So is there a possibility to have some randomized algorithm and get randomized?
It's not really, so there is randomization inbuilt. because we always take, maybe it didn't come out clearly, that's usually because I put everything was like in these modular things under the lemmas, so it didn't come out. But these distance approximation, they take a sample. Everything here is really randomized. It's kind of so sorry. This is something I wasn't saying. You know, there is an algorithm. There is not. I didn't even say that it's randomized. Maybe because I'm so used to it that you must work by, you sample vertices, you look at the induced subgraph, and but you sample them uniformly at random. This is so it makes it.
So this guarantees there is a delta. There is a probability delta in these guarantees.
So there is, everything here is just with high constant probability. If you want, and you can make it, 1 minus delta by repetitions, and taking, if it's the property testing, taking the majority decision. If it's distance approximation, taking the median value. So for us, it's stated without this dependence. But there is, you can enter in probability 1 minus delta. The answer will be approximately correct. So it's kind of, it is probably approximately correct type of thing. So it's not, it's not learning in the PAC model, but it's the same flavor and in terms of kind of conceptually.
I have a question. You mentioned that there's some work on sparse graphs. So is it like there's work on graphs of bounded degree and there's work on dense graphs, and then what about in between?
Oh, excellent. Right. This is so there is, so kind of, again, maybe a little historically. So this was kind of the first model, the adjacency-matrix first model that was studied. Even before people talk about property testing, there was, since it's more related to what people in combinatorics work. So this was the dense one, was the one that was studied a lot. Okay, so then you're right. One model will be the bounded degree. So then you will say, okay, everybody has degree at most D. You can look at your D neighbors. And then a general one, the one that kind of encompasses, I would say, everything, and will be the following: that you have a bound, or the number of edges, or you have a bound. It can be, and it's not bounded degree, but the sparsity depends on M. So let's say it's even sparse, but some vertices may have very high degree. And then the distance measure will depend on M. So it's the number of edges you are allowed to say remove as a function of the number of edges that you have. Right? So this is a model that, I like that model a lot, and it is the most general. There are various questions: what type of queries you're allowed. Is it only neighbors? Can you only go to your neighbors? Or maybe you can ask both neighbor and queries of this type. So there is work in this most general model. The results tends to be harder, because that's not surprising. Some even, I'll say, even there's sometimes you can get the whole spectrum between bounded degree and dense, and sparse in the middle. You'll get, so in bipartiteness, actually this is the case, that you can go from the bounded degree dependence on n is the square root, and the dense, it's no dependence, and in the middle it degrades. It degrades in a sense, in a good sense. I mean, the number of queries goes down as you become more dense. Yeah. Any other?
I have just like a really general question. So I guess the impression I got from the talks is that the best results are obtained by these sort of combinatorial observations. Is that the general state of the?
Okay, good point. Okay, so I would say that in the dense graph, though it's not. They're saying there are there algorithmic questions? Kind of, maybe, I don't know if this is what because it's. So first there is okay, I'll say two things. So one thing that's actually interesting in GGR, the paper that I mentioned before about partition properties. So in terms of the algorithm, they were simple. You just sample and you look at the induced subgraph. The analysis actually didn't use something like a known characterization, but actually worked from first principles about how, how could you show that if somebody is far, then it will be caught. So it's not always dependent on known combinatorial effects, but sometimes it is. I think in a sense, it's, I mean, I don't care, you know, what is combinatorial? It's always, you know, these definitions, what is combinatorial? You know, people say everything is combinatorial. But instead of the flavor of things, so for example, in the bounded degree of sparse model, there is more, the techniques will be, say, you know, you use random walks. So you will use things like what you know about expanders. So there'll be like a different set of tools that you will use. So that's kind of yeah, the spirit of things. So also in the bounded degree and sparse, there are also people from combinatorics working, and there are also combinatorial flavor to it. There's always in the graph, but in other objects then less. But I talked over only about graphs.
Thanks.
Okay, so unless there are more questions, let's all thank Dana again for the fantastic talk. Thank
you.
All right, and I thought maybe we can try a little experiment. I really miss this this time after the talk where you sort of walk into the lobby and you know, have a coffee with your friends. So in the chat, I'm going to post a link to the Simons Institute GatherTown, and anyone who wants to meet there, you know, I'll be there to have some small talk. So, okay.
Okay, so can you send it, because I can't see the chat